So this is a quickie intro video into how to do definite integration. It's going to be a how to make all the bits go rather than an explanation of why it is this way. If you want more about the proof and the whys, let me know, but this is a how-to. Good rat, Zeke. Okay, so this is a calculus thing, and the idea of definite integration. So indefinite integration is something like this. If I say the integral of x with respect to x, that's 1/2 x squared plus some constant of integration. But if I say the integral of x dx, and I put some limits on it, maybe 0 to 6, then that means, well, the way that you go about computing it is you have the integration-y bit. We can ignore the constant. I'll show you why in a minute. That's what you do to integrate x. But then we say that we evaluate this between 0 and 6. And what that means is you take this expression and you plop a 6 in. So I'm using square brackets for readability, for grouping purposes. So I'll take that 1/2 times 6 squared, and then I'll plop a 0 in. So 1/2 times 0 squared. So that's sticking a 6 into our expression, and then this is sticking the 0 into our expression, and you subtract the 2. And this is going to turn out to be 1/2 of 36, subtract 1/2 of 0, which is just 0, and the grand result is 18. Okay, so definite integration gives you a numeric value at the end. The interpretation of that number is the area under the curve, and this is what I mean. Sorry, I want that to stay in frame. Okay, so if I graph that function, it's y equals x. I picked a simple one. I'll show you a fancier one in a minute. Okay, this graph is going to be a straight line with gradient of 1. And if I go, my limits are between 0 and 6, and those are x numbers. So here's 0, and here's 6. The interpretation of definite integration is that it gives you area under this curve. So the area under this curve, the calculus tells us that that number should be 18. I can also see that I get a triangle, and the length of the base is 6, and the height is also 6. I know that that point has coordinates 6, 6 because I picked a very, very simple function. That's straightforward to see. So 6 times 6 times 1/2 is 18. Let's do another one. Okay, so suppose that you've got the function, I don't know, we'll pick x squared with respect to x. So I want to integrate x squared, and maybe I'll go from 2 to 4. I'm just picking numbers today. Okay, so that's going to mean, so you do the integration-y bit. So x cubed is going to integrate, x squared, give the game away. X squared is going to integrate as 1/3 x cubed. And I know that because if I differentiate to check, x cubed is going to give me 3x squared, but that 3 times the 1/3 will give me the number 1, and I'm back to x squared. If I said that too quickly, let me know. So there's the integration-y bit, and I need to evaluate it from my bottom limit of 2 to my top limit of 4. And that means stick a 4 in, so I've got 1/3 times 4 cubed. You don't have to use square brackets. Sometimes I use square brackets because it seems nice to write at the time, but you can use round brackets if you prefer. Then you're going to subtract, stick a 2 in, so 1/3 times 2 cubed. And now you shake out the arithmetic. So 4 cubed, 4 times 4 is 16, times 4 is 64. I'll stay in fractions because thirds don't make nice decimals. So I've got lots of 4, 64 thirds. 2 cubed is 8. 64 thirds subtract 8 thirds, which is 56 thirds. Okay, that's approximately 3 goes into 56. Once carry the 2, 3 goes into 26. Almost 9 times, but not quite. So I guess that's about 18 2/3. I think that's right. Send your complaints to bbc@london.com. Okay, so that's the area under the curve. Excuse the jump, I made a mistake and drew my diagram wrong, and I want to start clean again. So what I said was that the integral of x squared between 2 and 4 shakes out, sorry, it's not approximate, it is actually equal to 18 2/3. I didn't approximate that. That's exact. So that's the area under the curve between 2 and 4. And here's the picture, properly drawn this time, to show you that. Some days are good graph days, some days are not good graph days. So here's my x squared. Okay, I like to do little dashes because I'm not good at putting the pencil down and drawing continuously and having it look nice. So here's my x squared. Okay, a nice bowl-shaped function. That's y equals x squared. And I integrated from 2 to 4. Those are x numbers. So here's x equals 2, and here's x equals 4. Okay. And on the graph x squared, I know that the coordinates of this point are 2, 4, and the coordinates of that point are 4, 16. So the integral gives me this little snippet of area. Sometimes I think of it as if you have to carpet a floor, how much carpet would it take? Or if you're painting a funny shape on the wall, like you've got a stencil or something, how much paint would that be? And it's always area from the curve to the x-axis. I'm not giving you a proof of that, I'm just telling you that it's the case. There are good mathematical reasons, but that's not what I want to focus on in this video. I want to focus on how you do the integration and the interpretation of the number that you get. So this 18 2/3, that's the area under this curve to the x-axis. So that's 18 2/3. And to convince you that that's reasonable, if I connect these dots, I get a trapezoid. Excuse me, a trapezium. In the States you get a trapezoid, but I guess here in the UK you get a trapezium. Or a trapeze, I don't know. Okay, so this orange shape, that's a trapezium. And not to drag you through geometry, but to show you that 18 2/3 is a reasonable number, I know that the area of this trapezium is going to be, so the area of a trapezium, it's 1/2 height times the sum of the bases. I know I'm doing this quickly, you can look this up or ask me if you don't remember trapezia. So 1/2. H is the height of my trapezium, and that's between the parallel sides. So my height is 2. It's multiplying. And my bases are these 2 vertical lines, and that's my y height. So this height is 4, and this height is 16. So I've got 1/2 times 2, which is 1. 4 plus 16 is 20. So the area of the orange trapezium is 20. And the integration said that the area under the curvy bit down to the x-axis is 18 2/3, and that's reasonable. We have lost a bit of area, but not a ton. So 18 2/3 is a very reasonable area to get. So I'm not proving this 18 2/3 exactly, but I'm showing that it's a reasonable interpretation. Right, so I promised that I'd show you why that constant of integration doesn't matter. So when you do indefinite integration, you have to say plus c. But when you do definite integration, we don't put it in. And here's why it doesn't become necessary. You can put it in, but it will subtract itself out. This is what I mean. So let's go back to 2 for x squared dx. Okay, so I know that you get 1/3 x cubed, but what if we had a constant of integration? Okay, well, I still need to evaluate that expression between 2 and 4, which means stick in the 4, then stick in the 2, and subtract the two amounts. So when we do that, we're going to get our, we said that 4 cubed was 64 thirds plus whatever our constant was. Subtract 2 cubed was 8. Subtract 8 thirds minus, 8 thirds plus whatever the constant was. And when you subtract all these things, you're going to have 64 thirds plus our constant, subtract 8 thirds, subtract our constant, and you add it there and you subtract it there, and you didn't need to write it in the first place. So that's why we don't bother. We just take the 64 thirds and the 8 thirds, or whatever that calculation was. Okay, I want to show you a trigonometric example and a few more interpretee bits. Okay, so suppose you've got a trig function. So suppose you've got sine x dx, and I'm assuming that you understand radians. When we do calculus with trigonometric functions, we have to measure our angles in radians, because degrees, although I'm very partial to degrees, I'm quite a fan of degrees, but they don't play nicely with calculus because it's an arbitrary division of measurement. Radians are more inherent to what it means to be an angle, what it means to be a circle, and that's why the math comes out all clean when you play in radians. Again, I'm just telling you that, I'm not proving it. If you want to know more about that, let me know. Okay, so suppose you're integrating sine x dx, and suppose we're going from 0 to, let's go 0 to pi over 2. Okay, so I know that sine will integrate to negative cosine, and I need to evaluate that between 0 and pi over 2. And if you can just write that bit down, you're doing really, really well. I know that sine integrates to negative cosine, and I know that I need to evaluate that expression from 0 to pi over 2. If you can slap that down, you're doing really well. Okay, so to evaluate between limits means first plop in a pi over 2. So I have negative the cosine of pi over 2. Then I subtract, and then I plop in a 0. So negative the cosine of 0. Again, we're in radians. Remember, if you use your calculator, you have to put it in radians. Okay, I do this so much that I know these values. Pi over 2 and 0 are tidy trigonometric values. So because I use it so much, I happen to know it. So the cosine of pi over 2 is 0. So I've got negative 0. Then I'm subtracting. And I know that the cosine of 0 is positive 1. So I want negative the cosine of 0, so that's a negative 1. And I'm being really careful with my brackets, because that's going to be 0 subtract negative 1. Subtracting a negative is adding a positive, and our grand result is 1. I think that's spectacular, to have something curvy and wiggly, and yet the area comes out as a really clean whole number. That's saying, here's your sine wave, does something like that, on and on, both directions forever. Here's your y, here's your x. And 0 to pi over 2, sorry I've drawn it kind of tiny, pi over 2 happens right here. And it's saying that this area between 0 and pi over 2, so this really pretty archy shape, like that, has an area of 1, exactly 1. I think that's really elegant. You have a ton of symmetry here too. This other portion from pi over 2 to pi is also going to be 1, so the area of one hump is 2. It's just so pretty. It's just so pretty. Okay, I've said to you that integration gives you the area between a curve and the x-axis, and that's true. Here's two things to be aware of. If your curve goes below the x-axis, you're going to get a negative area. If your curve is above the x-axis, you'll get a positive area. I'm going to show you integrating from pi to 2 pi, and I'm going to show you that that comes out as negative 2. And then I'm going to show you that if you integrate from 0 to 2 pi directly, Well, you've got positive area and then you've got negative area. Integration gives you the net total area. So if you integrate from 0 to pi over 2, if you integrate from 0 to 2 pi, you're going to get a grand total area of 0. So if you actually wanted the carpet area, you have to be very aware of who's above the x-axis and who's below the y. Oh my gosh, you know what, it's so hot. I'm so sorry if you're struggling to follow me. I'm going to say that cleanly again. If you want the total carpet area, you have to know where your graph is above and where your graph is below the x-axis, and you have to put a break in accordingly. I'll write out the math to show you what I'm saying. Okay, so it is a warm day today, and my brain struggles when it's hot. I do not appreciate warm weather, unless I can be at the beach. Okay, we should do this in the sand with a big stick and draw out all the trig in the sand for everybody to see it. I would do that. I would do that for free. Okay, so here's your sine wave. I wonder if I'd get into the press if I did that. Have like a BBC photographer come take a snap. That'd be a cool way to be famous, wouldn't it? To be like the person who goes down and draws math on the beach. Maybe I should look to do that. Okay, so here's 0, here's pi, here's 2 pi. I'm assuming that you're comfortable with sine waves and radians, okay? Pi over 2 is where the peak happens for y equals sine x. Okay, so I know that if I integrate between 0 and pi over 2, I got an area of 1. Okay, so I want to show you, boy, that really stands out poorly, doesn't it? It's an area of 1. Okay, so I want to show that integrating from pi to 2 pi gives you -2 for the area. So here's my integral from pi to 2 pi sine x with respect to x. Well, sine, that's minus cosine when I integrate. And I need to, you can put round A brackets, but it's better notation to show that you need to evaluate it from pi to 2 pi. Square brackets are nice for this kind of notation, but then when you pull it apart into its separate pieces, you can use round brackets. So, minus the cosine of 2 pi, subtract minus the cosine pi. Again, I do trig all the dang time, so I've got these memorized. You can use your calculator, and that's absolutely fine. Just remember to put it in radians. Okay. The cosine of 2 pi is 1, so I've got -1 in the first bit. Subtract. The cosine of pi is cosine goes like this. The cosine of pi is -1. This little sketch I did here, this is another way I remember the values. I know that cosine starts high and ends high, and that's a full 2 pi cycle. So halfway in between is pi. So the cosine of 2 pi is +1. The cosine of pi is -1. That's a nice cheat. Okay, or use your calculator, it doesn't matter. So using that cheat, so the cosine of 2 pi is +1, so I've got -1, subtract negative the cosine of pi. The cosine of pi is -1, so I've got -1. And this is where all your mad skills with negative numbers comes into play. So my first bit is still a -1, and I'm still subtracting. Okay, now I've got -1, that's +1. So I've got -1, subtract 1, which, behold, is my -2. And a negative value is when the area is below your curve. That's quite nice. I promised you that I'd show you 0 to 2 pi. And that should come out as a net total of 0. So integrating from 0 to 2 pi, sine x dx. So we know that that's negative cosine. I want to evaluate it from 0 to 2 pi this time, which is going to be minus the cosine of 2 pi, subtract minus the cosine of 0. The cosine of 2 pi is +1, so that's -1 again. Subtract. The cosine of 0 is a +1. It's a positive 1 this time, so I'm subtracting negative 1. It's a lot of negatives to subtract. Cosine 0 is positive 1. That's that negative, and that's the subtract. So I've got negative 1, subtract negative 1. Subtracting a negative is adding a positive 0. So the net area between 0 and 2 pi, the net area between 0 and 2 pi shakes out to be 0. So if you ask a mathematician, how much carpet do you need for these, between 0 and 2 pi, a mathematician will say 0. You need to go to the store and you need to buy 2 units of carpet, and then you need to buy negative 2 units of carpet, and that's a grand total of 0 carpet, so you might as well just stay home. And anybody sensible will say that's ridiculous. You should split it here and realize that that's 2 and realize that that's another 2. It's just below the axis, but you still need carpet, so you need to buy 4 units of carpet. And then you can fight about it over a beer or something. Okay, that's what I wanted to say.